Okay, so what we're talking about today is something known as refraction. And one of the big rules about refraction deals with something known as Snell's law. So let's start with defining what refraction is. Now, here's what I want you guys to imagine. Let's say that we have regular air that you breathe, and then you have some water that's still, that means it's like not moving around, there's no waves, nothing like that. It's just perfectly still water. What happens when we were to shine some light onto the surface of that water? First, let me draw a line that is perpendicular to the surface. From this point on, I'm going to call it normal to the surface. Okay, so just to be clear, when I say normal to the surface, that means perpendicular to the surface. Anyway, so we know from the law of reflection, right, that if we were to shine some light onto a shiny surface like water is definitely shiny, some of that light will be reflected at an angle that is exactly equal to the angle in which light came in with. All right, that's the law of reflection. Now, normally when you're talking about perfect specular reflection, all of the light gets reflected. But in the case of something like this, that's not really what happens. So you get some of the light coming in, some of it gets reflected, and then the rest of it ends up getting refracted. So refraction means light gets bent through when it travels through some sort of material. Okay, it gets bent. So we have a couple of angles here. Theta I is the angle of incidence. So the angle in which the light ray comes in with. And we always measure it to align normal to the surface. And we know from last time, not last time, but the time before last, that the angle of incidence has to be exactly equal to the angle of reflection. That's, of course, the law of reflection. But now we have another angle called the angle of refraction. So since both of those things start with the letter R, I use the capital R and a lowercase r. So theta capital R is going to be the law of refraction, for now at least. Now, how the light gets refracted is going to be dependent upon what type of material is the light going through. So now let me share with you another screen to give you a better idea of how this works. So I hope you guys can all see this. It's a similar drawing to what we had on the iPad. And basically, here's some light. And as you can see, some of it is getting refracted and some of it is getting reflected. Let me show you another way. So we have air and glass. So let me change this to water so it's similar to what we were doing before. And let's look at the angle. So my angle of incidence here is, let's make it 60 degrees, just to give it a random number. So we see that the angle of incidence is 60 and the angle of reflection is also 60. Of course, that is due to the law of reflection. But the angle of refraction down here is 40.6. And again, we measure it to a line normal to the surface. So the question now becomes, okay, how do I figure out what this angle is? What equation can I use to figure that out? Now, let me keep this angle up here at 60 and let's look at some different materials. So let's say glass. Notice that the angle changed. Mystery A, angle change. Mystery B, angle change. Custom, I could change this number over here, N. You'll see what that means in just a little bit. But notice that if we were to make both materials air, there's no refraction happening. And as we change the material, right, make that index of refraction bigger and bigger and bigger, we could deflect that light more and more and more and more. So the higher this number right here is, the more refraction you have happening. So let's give a definition to what this thing is, the index of refraction. And then we can figure out how those numbers compare for different materials. One more thing I want to show you before we get into the math is it doesn't matter what type of light it is. I'm changing the color and therefore changing the frequency and wavelength. It has no effect on the way that the light is bent and reflected. In fact, if we were to take this even to a higher frequency like UV and up, this would still happen. Same thing with the other extreme. A lower frequency, infrared and lower, same thing happens. It doesn't really affect the way that light is bent. Cool. Now, let's go back to the lesson over here. So we have our incident angle, our reflected angle, and our refracted angle. And basically what we're going to try to figure out today is this guy right here. What is the angle of refraction? All right, let's take all this stuff off. First, let's define what the index of refraction is. It's a property that all transparent materials have that is a measure of, well, it's a ratio of the speed of light over the speed of light inside of that material. So it's a speed divided by a speed, therefore you're just going to get a number. It's dimensionless. And it's always going to be a number not less than 1. I don't know why I wrote that. It's actually greater than 1. My mistake. It's always going to be 1 or bigger. If your index of refraction is 1, that means that the two materials that the light is traveling through are the same materials, or it could mean that there is just no refraction happening whatsoever. Okay, so it has to be 1 or bigger. So again, this is something that is dependent upon the material that you have. So let's look at a couple of indices of refraction for different materials. Now, let's say you have ice at 0 degrees Celsius, so like perfectly frozen water, ice. The index of refraction becomes 1.309. You have different kinds of glass. So crown glass at a standard temperature of 20 degrees Celsius, which is about 70 degrees Fahrenheit, is 1.520. Water at a standard temperature, 1.333. Air at standard temperature and pressure. Pressure also has an effect on this, but let's not get too into that. It's a 1.000. There's more decimals after that, but we could approximate it to 1.00. Diamond, 2.42. And let's add one more to this, something known as the vacuum, which is literally nothing. That one is exactly 1.00. We could do this forever. Okay. But if we're talking about regular air, we could approximate it to 1.00 as well. Now let's look at the law that dictates how these angles work. Okay, so let's say we have our two materials, material 1 and material 2. Each one of these guys has its own index of refraction, N1 and N2. As my light ray is incident upon the material, on the second material, it gets refracted. So that first angle of incidence will be what I'm going to call theta 1. and the angle of refraction would be theta 2. The formula that dictates how this behaves is known as Snell's law, which looks like this. N1 sine of theta 1 equals N2 sine of theta 2. So using this formula, using Snell's law, you could determine, if you knew what the angle of incidence was, and if you knew the two indices of refraction, what is going to be the second angle. Another thing that you could determine is, okay, let's say we only know one index of refraction, but we know both angles. You could figure out the other index of refraction. Usually you would use it in that way because sometimes you'll be dealing with some unknown material. Okay, this is the only formula we need for today's lesson. N1 sine theta 1 equals N2 sine theta 2. Let's look at some examples on how to use it. Example 1. Says here, a yellow light ray traveling through the air strikes a smooth, flat slab of crown glass at an angle of 30 degrees to the normal. Determine the angle of refraction through the glass. So here is a picture of what this looks like. You have your air. We could approximate the index of refraction to be 1.00, and the crown glass has an index of refraction of 1.52. We know that theta 1 is 30 degrees, so we got to figure out what theta 2 is. Okay, here we go. So here's what we know. Again, we know that theta 1 is 30. We know that N1 is approximately 1.00. We know that N2 is 1.52. We want to figure out what theta 2 is. So here's what we do. Using our formula, right, N1 sine theta 1 equals N2 sine theta 2. We just plug the stuff in. All right, so we got 1.00 times sine 30 equals 1.52 sine theta 2. On the left-hand side, we got 1 times sine 30, and I'm using my calculator here. It's equal to exactly 0.50. Let's leave it at 3/16. 1.52 sine theta 2 on the right. I'm going to divide both sides by 1.52. That cancels out. And then I end up with sine of theta 2 equals 0.3289. And there's a few more decimals after that, but we could just leave it there. Okay, so I have, let's see, 1, 2, 3, 6 people in here right now. Out of the 6 of you guys in here, do any of you guys know what to do next? How do I get theta out of a sine theta? What should I do? You can write it in the chat if you think you know. Okay. What we need to do, and you can do this on your scientific calculator, is the inverse sine, like this. You do it on both sides of the equation. So what ends up happening on the left-hand side, when you do the inverse sine of sine, those two functions cancel each other out. And you're just left with the stuff inside of sine, which was theta 2. Now, if you're using decimals, let me go ahead and show you what that looks like. I'm going to share that screen with you guys as well. All right, that's really big. That's better. So you could just type in sine -1, or you don't like doing that, you could go to function, and then you could just type this one in here. So we had 0.3289, and there's your angle right there. All right, let's go back to the iPad. And there you have it. The angle of refraction is 19.2 degrees. So if we go back here, this angle right here will be 19.2 degrees. So again, if you are ending up with sine of theta on one side and you want to get theta, on your calculator, do sine -1. This is known as inverse sine or arc sine. All right, let's look at another example. This one's interesting because we're dealing with a different type of situation where you have a material that is kind of sandwiched in between another material. So you have your light ray traveling through one material, it refracts through another piece, and then exits on the other side back into the original material. Something like this. For this problem, our laser is coming in at an angle that is 40 degrees to the normal. Now, for some reason, I wrote here 30 degrees, but it's supposed to be 40 degrees. Anyway, it's traveling through air. It hits this plexiglass, which has an index of refraction of 1.51. And then it exits at the air at some unknown angle. Now, there's an easy way of doing this, and there's a harder way of doing this. The easy way is to use geometry and symmetry. If we have a uniformly thick piece of glass, right, as you see right there in the middle, we know that this theta2 over here and this one have to be the same because it's like taking a rectangle and then drawing a diagonal line across. The two triangles that form as a result of that are, of course, congruent to each other. We know that from geometry. Now, we can reasonably suspect that this angle and this angle will end up being the same. Let's go ahead and prove that. Now, let's say, okay, so we started with N. We started with N1 equals approximately 1.00, and 2 equals 1.51. Theta 1 equals 40 degrees. Theta 2 equals, we don't know, but that doesn't matter because what we need is theta 3. So we're going to have to figure out what theta 2 is as an intermediate step so that we could then apply the same rule to theta 3. All right, so let's go ahead and do the same thing that we did before. 1.00 sine 40 equals 1.51 sine theta 2. 1 times sine 40 gives me 0.6428 approximately. 1.51 sine theta 2. Divide both sides by 1.51. That crosses out. So that I get sine theta 2 equals 0.42569 approximately. Theta 2 ends up being the inverse sine of that number. So according to my calculator, that is 25.2 degrees, more or less. So let's keep that answer in mind for now. Let's erase this and go back here. We now know that this angle is 25.2 degrees. And this one is 25.2 degrees as well. This is going to end up being your angle of incidence through the plexiglass. And this right here is your angle of refraction that we're going to need. So the way that we're going to figure this out is to just apply the rule one more time. Let's go back here. So 1.51 sine of 25.2 degrees equals 1.00 sine theta 3. We're able to do this because we go back to the picture. Over here, we're going to have our first material, and over here, we're going to have our second material, our incident and our refractive. Okay. The incident material has an index of refraction of 1.51. All right, so we're gonna go ahead and apply the same thing. (1.51) times sine of 25.2 is 0.6427 9. Yeah, 64279. 1.00 sine theta 3. Divide both sides by 1. Of course, that's not going to do anything to the left-hand side. Sine theta 3 is equal to 0.64279. Do the inverse sine of that number. And then we have a curious result here. Theta 3 is equal to 40.0 degrees. Now, that ends up being exactly equal to the angle that the light ray started with. So if we go back to the picture, one of the predictions that I made was like, okay, I think due to the symmetry, due to the geometry, I think that theta 3 will be exactly equal to theta 1. And now we see through Snell's law that this is, of course, true. So here, allow me to make a statement. Let me erase all this. So let's say we have N1, N2, and then N1 again, right? What's going to end up happening, we have our light ray, and we have a, let me put it down here. Our light ray. What happened? Sorry, guys, I'm having an issue here. Here's our light ray. It's going to diffract like that. So let's say that this is your angle of incidence. Here's your angle of refraction. This one is going to be the same. And this one is going to be your new angle. If the materials on the left and right are the same material, then theta 1 is going to be equal to theta 3. And we just proved that using Snell's law. And let me make one more statement. Let's say we have 3 different materials. N1, N2, and N3. This is going to be a little bit different. Here's your incident light ray. It's going to refract a little bit. And then it's going to refract again at some other angle that we don't know. The way we work this one out is like this. Here's our theta 1, our theta 2. These two, of course, have to necessarily be the same. And then here's our theta 3. If you got if you have 3 different materials, and a situation like this, you could imagine it's like going through air, then going through water, and then going through glass, right? Actually, no, it makes more sense to say water through glass than through air. Like imagine having a glass of water sitting on your table. The light ray that's hitting the glass is going through the air, and then it refracts through the glass, and then refracts even further through the water, right? Use Snell's law 3 times. N1 sine theta 1 equals N2 sine theta 2, which is going to be even further equal to N3 sine of theta 3. So you could use any of these equal to each other. You could say N1 sine theta 1 equals N2 sine theta 2. You could say N1 sine theta 1 equals N3 sine theta 3. Or you could say something like N2 sine theta 2 equals N3 sine theta 3. Think of it like A, B, and C, right? A equals B equals C. If A is equal to B, then and B is equal to C, then A is equal to C as well. This is the transitive property, of course, in math. So there's going to be a question like this on the homework as well. There isn't really a point for me to show you an example of doing this because it's the same math. But just know that if you have 3 different materials, you could use the Snell's law equation in this way. And that is it from me today. So just to recap what we talked about, let me go back to the other slide. Snell's law is the equation that dictates how a material refracts through some other material. It is the formula N1 sine theta 1 equals N2 sine theta 2, where N1 is the index of refraction of the first material, theta 1 is the angle of incidence, N2 is the index of refraction of the second material, and theta 2 is the angle of refraction. When you have more than 2 materials, 3 or more, you could just continue adding equal signs to this. So let's say you have 3 materials, N1 sine theta 1 equals N2 sine theta 2 equals N3 sine theta 3. and you could add more and more, as many as you need. For the homework that you're going to see when we get off the call, there will be one problem dealing with 3 materials. The rest of them only deal with 2 materials. All of the indices of refraction will be given to you in the homeworks, and the angles, of course, will be given to you as well. So, having said all that, let me stop the screen share. Let me also